Okay, here's a quick overview of what you missed if you missed class on Tuesday. For notes, we started class with this opening question: who's facing the worst headache? You've got two people here and a flower pot that's coming in and hitting them on the head. The first rebounds at the same velocity that it comes in at, and the second one just sticks. It just comes to a stop. So take a second, see if you can answer that question and justify why. And the correct answer is the top one is a worse headache, and here's why. As the pot's coming in, we could multiply the velocity times the mass here and get a momentum vector going down. This would be my initial momentum of the pot. And then the final momentum is going to be that same vector. It's going the same velocity, it's the same mass, it's going to be the same length of vector, just going upwards. Which means my change in momentum is going to be this vector, twice as long in the upward direction. And my change in momentum is equal to my impulse, which is equal to my force times my change in time. If we do the same thing on the bottom one here, we have an initial momentum that's equal to the momentum above in this top one, but at the end there's no momentum, which means my change in momentum is just going to be this vector, equal in length to my initial momentum. And again, the change in momentum is equal to my impulse, which is equal to my force, my average force, times my change in time. Well, if I have a greater impulse up here, twice as large, and it's the same amount of time that the pot's interacting with both heads, this must have twice as big of a force, which would be the one that would hurt worse. And that's your answer there and how to think through it. Okay. So the rest of the class we looked at collisions, and this is kind of just a quick understanding of collisions. You guys did this on a mastering physics problem, deriving how momentum is conserved. But just consider a dump truck hitting a Prius here. The two collide in the middle, and when they collide, the dump truck and the Prius both have a force acting on each other, and the force that the truck exerts on the Prius is equal and opposite to the force that the Prius exerts on the truck. We know that from Newton's third law. Now the effect of those forces is not going to be equal because this is a smaller mass, a little m, and this is a big mass, a big M. If they're equal forces, the acceleration of the car will be greater, but the actual force is going to be the same. And if we are looking at this collision in terms of impulse and momentum changes, to calculate the impulse, we want to know what's the force and what's the change in time. Well, for both objects, they have the same amount of time that they're touching each other, so that's going to be the amount of time that the force acts. And if they have the same force but in opposite directions, according to Newton's second law, that means that the momentum change for the truck, or the impulse, is equal, same force, same time change, to the momentum change for the Prius, same force and same time of interaction, but in the opposite direction. Which means if we consider this as a system, and we treat the system as the truck and the Prius, we can calculate the impulse of the system by adding the impulse of the truck to the impulse of the Prius. And since they're equal and opposite to each other, we get this: the impulse on the system is equal to 0 kilogram meter per second. Which means my change in momentum for this system, if we consider the truck and the car together, is also 0. It has the same momentum to start before the collision as the momentum after the collision. And that concept allows us to make really complex collisions a little bit more simple to solve. So we can say the change of momentum for this truck Prius system is going to be 0, so I can write it like this now: my momentum initial equals my momentum final for this collision. And that's true for all of our collisions, as long as we consider every collision as an isolated system. So this is kind of a concept we're going to use over and over again this year, and this is our second conservation concept. We have a conservation of momentum, which is what we're going to look at here with collisions, and it's similar to our conservation of energy. Both of those get conserved in certain circumstances. So for collisions, if you have a collision in a problem or an explosion, always include everything that runs into each other, everything that bumps in your system. If you include everything that bumps, that means we're including all the forces right here that have the same time interaction, which would cancel out impulses, which would mean our system has no change in momentum. So you always want to include everything that runs into each other in the system. And if that's true, then your impulse on your system will be 0, and momentum will be conserved both before and after the collision. Now that's only true if you have an isolated system. The system has to have no external forces acting on it, so we don't have an external change in our momentum. When you're considering systems, it's good to remember that the momentum of a system is the sum of all of the individual momenta of each object in the system. And so if we want to know the initial momentum of a system, we would take the initial momentum of object A, add it to the initial momentum of object B, and so forth until we have all the objects out to object N added up in our system. So we can have a system with multiple objects. We just need to add those up. Remember, it's a vector, so we have positives and negatives here depending on the direction they're going. So let's consider a simple problem here. Let's consider a train car. I'll just scroll down to our picture here. Here's our setup. You have a train car with an initial velocity of 10 meters per second coming in, and it collides with 4 other cars that are initially stationary. It connects to those 4 other cars, and all 5 of these train cars have some final velocity moving off together on the tracks. And we want to know, what is this final velocity here? Well, to do that, we need to look at our collision by considering all of the objects that collide. So your system would be our car moving, plus all 4 of these cars that are stationary. And we include all of those in the system before and after our collision. So to do that with momentum, we want to say the momentum of our system initially equals the momentum of our system finally, because the impulse due to the forces of this collision are 0. Our momentum of our system initially is just the momentum of car number 1 that's moving initially, plus the momentum of our 4 cars initially. Well, the 4 cars are at rest, so I can say my momentum of my system initially is the mass of the moving car. We'll just call it m right now. I know the mass is some value up here, 18,537 kilograms, but we're going to see that the masses actually cancel out here. So my mass of my moving car times its velocity, plus 4 times m, the mass of the stationary cars, times their velocity. Well, that's 0. And so I just get 10 m. And this would be better written at 10 meters per second times m, my mass. The momentum of the system final is going to be the sum of all these masses. If it moves as one object, all of these would be moving together with the same final velocity. We can treat this as one big object with one mass. And so the combined mass here would be m plus m plus m plus m plus m, which gives me 5m for my mass, times the final velocity, which is what I want to know. And then I can set my initial momentum, my 10 times m, equal to my final momentum, 5m times v, final, and my masses cancel, and I get a final velocity of 2 meters per second. So these cars here now are traveling at 2 meters per second to the right. And if you look at just a purely momentum vector approach here, the momentum vector to start here is going to be 10 times my mass, my velocity times my mass, and here I have 5 cars. So if I calculate my momentum, here's momentum initial, my momentum final, it's going to be 5 cars times their mass times my velocity of 2 meters per second. And you get the same thing, 10m. So my momentum doesn't change in my collision, which is what we want. Our next problem that we'll look at here are 2 carts on a track. And again, let's just look at our picture here. Cart A is headed towards cart B. Cart A has an initial velocity of 3 meters per second, and cart B has an initial velocity of 6 meters per second in the negative direction. That's before a collision. Just after the collision, we measure the velocity of cart A to be 2 meters per second to the left, and we want to know what's the velocity of cart B. Same approach. I want to know what's the momentum of my system initially. Well, initially we have 2 objects here, each with mass m, m times 3 meters per second would be the momentum of cart A, and I'm writing that in right here. And m times a negative 6 meters per second would be my momentum of cart B. If I add those up, you get a momentum of negative m times 3 meters per second for a total system momentum initially. The momentum of the system finally would be cart A's momentum, which would be negative 2 meters per second times m, plus cart B's momentum, which would be its mass, m, times its final velocity, VB final. Setting those equal to each other, momentum of the system initially equals momentum final, I get this, negative m times 3 meters per second equals this equation here. And all of my masses cancel, add 2 meters per second to the other side, and you get negative 1 meter per second. So my final velocity of cart B is a negative 1 meter per second. And that maintains the same momentum before in the system as after. And that's how you approach every momentum problem. The third example we looked at was two ice skaters pushing off from each other. If they're starting from rest, they're both on a frictionless surface starting from rest. My momentum initial for my system is 0, and that means my momentum final for my system also needs to be 0. And you can see if you can solve this one and get our answer. This is our answer here. The man needs to be moving to the left at negative 1.53 meters per second. This was the more complex problem we solved in class, and this particular problem has a 10-gram bullet fired into a 1 kilogram wood block. This is a classic momentum problem. The bullet embeds into the wood block, and when it embeds, it comes to a halt in the block. So the block and the bullet move together at the same velocity, and then that block and bullet system slides across the floor for 4 meters before coming to a stop, and the floor has a coefficient of kinetic friction of 0.20. And we want to know what's the bullet's initial speed. What was V initial right here? I'll just call it VB for the bullet. Well, we've got two things happening. We want to break this problem into two different before and afters. And the first is just before your collision and just after the collision, immediately after collision, before the block slides. And the reason you want to do this before the block slides is because to conserve our momentum, we have to have a system that has no external forces. And so we want this bullet to embed in our block, and we're neglecting the friction that the block has with the surface. Because this occurs in such a short time period, we're just going to treat it like that has its own event. The collision is its own event before the friction starts to happen. And we can figure out what is that velocity at the start of this before it starts to slide. So that would be the velocity at the end of our collision. And we're going to call that V final after the collision. That means the momentum of the system initially has to equal the momentum of the system finally before we have friction involved. And the momentum of the system initial is just the bullet, it's the only thing moving, convert its mass into kilograms times its velocity VB. We don't know this, is what we're trying to solve for. And that equals the momentum of the system final, which is the mass of our system, the bullet plus the block. They move together as one mass with one shared velocity, and so we can combine their masses times the final velocity. Well, we don't know the velocity of the bullet, and we don't know the velocity of the block bullet system after the collision. But we can use this extra information, the 4 meters and our kinetic coefficient of friction, to calculate what this final velocity needed to be in order to travel 4 meters across the floor. And there's two ways to do that. You could do a work energy approach, where you're changing kinetic energy for the block has to be equal to the work of friction. So my block has some initial velocity, we called it VF from the previous part of the problem, and it travels 4 meters before getting a final velocity of 0, which means my kinetic energy final is going to be 0. And I can solve this equation here with the work of friction being equal to the force of friction times its displacement. if you substitute all those variables in here, my kinetic energy